Okay, so we're talking about sensitivity, specificity, net sensitivity, net specificity, and positive predictive value. And essentially, what we're talking about is assessing the efficacy of diagnostic testing or diagnostic tests. So, again, obviously, a good diagnostic test, we want to be able to root out as many people with the disease as possible, and that is sensitivity, and exclude from further testing as many subjects as possible that do not have the disease. So, we want to make sure that our test is correctly identifying those people that actually do have the disease. And we refer to that as sensitivity. So, it's the probability that a test says that a person has a disease when in fact they do actually have that disease. And you should probably write down that formula at the bottom there. The number of true positives divided by the number of true positives plus the number of false negatives. Okay, so that will make a little bit more sense when we take a look at some of these problems. Specificity, the probability that that a test says that a person does not have the disease when in fact they do not have that disease. So we want to make sure that that test is correctly identifying people that do not have the disease. And again, I would recommend that you write down this formula as well. The number of true negatives divided by the number of true negatives plus the number of false positives. Okay, so this is what we're going to be looking at, these 2 by 2 tables that we see at the bottom right corner here. And this is what, when I'm referring to true positives and false negatives and things like that, this is what we're going to be looking at. So when we plot this data, we'll see that the first column is those people that actually do have the disease. The second column is people that do not have the disease. This first row is people that tested positive on this test. And the second row is those people that tested negative. Okay, so this top left corner, true positives, people that actually do have the disease and they tested positive. False negatives would be people that actually have the disease but tested negative. False positives, people that do not have the disease but came up with a positive test. And then, of course, true negatives, people that do not have the disease and came up as negative. So, for obvious reasons, we don't want to have many false positives. We don't want to have any false positives or false negatives for a variety of reasons. The athletes are always concerned about false positives when they come up hot for drug tests. And there's other reasons as well. It's very stressful to get a diagnosis that you have a disease when you don't really have a disease. False negatives, again, if you get a test that says you're negative and it turns out you actually do have cancer or whatever that disease is, you just spent the next 6 months or a year not getting treatment because you thought that you did not have that disease. So concerns for both false positives and false negatives. Obviously, depends on the situation, which one is more serious. So I have some problems here. I'm actually going to uh, escape out of here for a second, and we're just going to work on these problems here. So I have my Google calculator set up. All right, so physical exam was used to screen for breast cancer in 2,500 women that we know had breast cancer. Um, and then there were 5,000 control women that did not have breast cancer. And essentially, what they're doing is just determining how accurate a physical examination is in picking up a breast tumor, a tumor in the breast. Okay, so 25,000 women that have the disease, so we can put that in here. 5,000 women that do not, that's our control group. The results were positive. In other words, a mass was palpated in 1,800 cases. So 1,800 goes right here, and in 800 control women. Okay, so there were 800, 800 false positives, 1,800 true positives. Okay, and then simple arithmetic will give us what's it, 2,500 minus, that's 700. I shouldn't be doing this in my head, but and then 4,200 for our true negatives, and then our false negatives would be 700. Um, okay, so we know that our sensitivity is true positives divided by true positives plus false negatives, or another way to say this is our true positives divided by the total number of people that have the disease. So 1800 divided by 2500, and that gives us a sensitivity of 72%. Okay, specificity, um, true negatives divided by true negatives plus false positives. So in other words, the number of true negatives divided by the total number of people that actually do not have the disease. Okay, so 4,200 divided by 5,000, 84%, which makes sense. Okay, all right, so that's pretty much it. All right, these are pretty straightforward. Some of the other ones are going to be a little bit trickier. All right, so um, there's a couple different ways that we can do this, and we're going to take a look at those in a minute here. So that's the first way, and I have some practice problems that you can do with those. This is basically what we just looked at, except I filled in the block for us. We're also going to be taking a look at positive predictive value and negative predictive value. So it's the same kind of concept, somewhat similar anyway. It's also called the precision rate. So it's a similar formula, except that for our numerator, for our positive predictive value, well, our numerator is going to be the same. It's the true positives. It's the denominator that's different. The denominator is going to be the total number of people that tested positive. So rather than using the denominator as the total number of people with the disease, it's the total number of people that tested positive. Okay, so in this case, it would be 475 divided by 500. Negative predictive value, same kind of concept, true negatives, so the same numerator, but the denominator is going to be the total number of people that tested negative. So the denominator is going to be different. Okay, so true negatives, 94,550 divided by 99,500. That gives us a negative predictive value of 95%. Okay, so again, I have another, we can work out this formula, or excuse me, this problem here. So in a population of 2,000 people, so we can put our total here, 2,000. Tells us the disease prevalence is 10%. So 10% times 2,000 is going to be 200, right? I think. Okay. The specificity and the sensitivity are both 98%. Okay, so in the last problem, we had to calculate out what the sensitivity and the specificity were. In this problem, the sensitivity and specificity are given, and we need to fill out this chart, okay, which is a pretty common way that we want to approach this. Okay, oops. All right, so we have our total. We have the total number of people with the disease and the total number of people without the disease. Okay, we're told that sensitivity and specificity are both 98%. All right, so if the true positives are 98% of 200, pretty straightforward, 200 times 0.98, 196. When you're doing this, if you do come up with a decimal point, it's best practice to round off to a whole number. Again, since we're talking about human subjects here. 1,800 times 0.98, and that's going to give us 1764. Okay, so true negatives 1764, true positives 196. False negatives is going to be 4, and I'm going to have to, what's that, 36, I think. Again, I'm going to double check that just because my math isn't. There you go, 1,800. All right, I got it right. All right, so positive predictive value. Remember, it's going to be our true positive, essentially divided by the total that tested positive. Okay, so 196 plus 36, 232. And I might as well do this one here, 1768. Oops. Okay, so positive predictive value, 196, divided by 232. Positive predictive value is going to equal, we'll round that up to 84.5%. Okay, negative predictive value, true negatives divided by the total. Uh, 1800 divided by 2000. And we got 90%. Okay, so these are pretty straightforward. Again, I have practice problems that are posted that will give you the opportunity to work this both ways. You know, the first one where you have to calculate out the sensitivity and the specificity when all the data is given, and then the second type of problem where you're given the sensitivity and the specificity and you need to fill out these blocks. Okay. Let's take a look back at our presentation. I think I got everything here, but let's take another look. Yep. Okay, so the next step is net sensitivity and net specificity. And these are a little bit more complex. Basically, what you're doing is, it's a lot easier for me to just jump right into the mathematics for this. So that's what we're going to do. Basically, what you're doing is you're using two tests. So you're exposing a population to two tests. And the idea here is that we call it two-stage screening or sequential screening, is that the first test that you use is not real accurate, or it's cheap, less expensive, it's not really invasive. It's also not as accurate as you would like it to be. So what happens is you screen a large population with this first test, and then anybody that tests positive on this first test gets called back for a second test. Okay, so a pretty good example would be the over-the-counter pregnancy tests that they sell in the supermarkets and the drugstores. A lot of women will take those, come up positive on those, and then go to the doctor for further testing. But there's a lot of, I'm sure, different types of testing out there that are used that would be good examples of this. Okay, so we have a population of 10,000 people. Disease prevalence is 5%. So I'm just going to calculate this out. 0.05 times 10,000, 500, right? Which gives us 9,500 as the total without the disease. Okay. Let's see. Sensitivity of 70%, specificity of 80%. Okay, so to fill out this block, 70% times 500 is going to give us our true positives, 350. Okay, and then again, basic arithmetic will give us 150 here. For our true negatives, the 80% of 9,500 will give us our true negatives, times 0.8, 7,600. And then I'm going to have to, I should be able to do this in my head, I apologize. Minus 7,600, 1,900, okay? Okay, so we have our first chart figured out. We're not going to really need the positives here, or the totals, but it's best practice to fill these out as well. 2250, and then what's that? 750. Oops. Okay. So again, keep in mind what we're doing here for this test. Anybody that tested positive is getting retested. Okay. So all we need to do is transfer this information from this top row down to this total column down here. Okay, so 350, 1900, and 2250. Okay, then we're given the sensitivity and the specificity for test B. All right, they're both 90%. So again, pretty straightforward. 350 times 0.9 is going to give us our true positive for test B. True negative for test B, 1900 times 0.9, 1710. All right, and then again, what's that, 35, I think? And then 190. Oh, whatever. I know, I always try and do these numbers in my head, and about 80% of the time I'm right, but I should double check. Okay, so there we go. So the formula for finding net sensitivity is we take the number of true positives from test B, so in this case it's 315, divided by the total number of people with the disease. And to get that total number of people with the disease, we need to go back to test A and look at this this number here, 500. Okay, so when we do that, we get 315 divided by 500, and let's calculate that out. 63%. Okay, and then, oops, let's see what we have here. Let's see if I can. So for the net specificity, number of true negatives from test A, 7,600, plus the number of true negatives from test B, 1710, divided by, this should say the total number of people without the disease, or it's a total number of true negatives. There you go. That makes a little bit more sense there. So number of true negatives from test A, 7,600, plus true negatives from test B, 1710, divided by the total number of people without the disease, 9,500. Okay, so let's do that one. 7,600 plus 1710, and then we do, is that right? No, sorry about that. 7,600 plus 1710 divided by 9,500, 98%. Okay, so 98% net specificity. Okay, so one of the ways that students will sometimes use, they can use this as a check. If you take the sensitivity from test A and multiply that by the sensitivity from test B, 0.7 times 0.9, you get 63%. Okay, so that's a pretty good check. Some people will try to just do that and give me that number as the final answer without doing the math, and I will not accept that. You need to do the whole problem. But that's a pretty good check just to make sure that you actually got the question right. Okay, so just for further clarification, there's two different types of net sensitivity and net specificity problems that are in the textbook. The one is sequential testing or two-stage testing. That's what we just covered. They also cover simultaneous testing, which is a whole different problem. It's a whole different set of calculations, a whole different set of formulas. We will not be doing simultaneous testing for net sensitivity and net specificity. Okay, so you can just skip over that part in the textbook. We are only doing sequential testing, two-stage testing. And the problem on our test is going to look very similar to this. Okay? All right, I hope this was helpful.